afternoon. Let's quiet down so we can get started. I'm a little late today because I came right from discussion. Are there any questions before we get started? Anybody? All right, we're going to work on chapter 18. It appears that we are going to have to skip the nucleophilic aromatic substitution reaction part of this chapter. I will cover it next quarter when we do chapter 25 if you have my class next quarter, but we're not going to have time to cover it. So I'll let you know when we get to that section. Where did we leave off last time? We were drawing a bunch of resonance structures. We were trying to prove, we were trying to see why electron donating groups give ortho and para products. So we did the ortho, and what we saw is that we can make a really nice resonance structure here. This one is especially stable. What did you just do? Okay, doesn't want to do that for some reason. We'll just continue it right here. Especially stable resonance structure. Why is it especially stable? Every atom has 8 electrons. Every atom has an octet, and we have an extra covalent bond. So especially stable, all atoms have octet. Plus we have an extra covalent bond. So we saw as we were doing electrophilic aromatic substitution on benzene, we have 3 resonance structures. When we have an electron donating group, we have 4 resonance structures. Okay, so that's going to make things especially stable. That's going to mean that we have a lower energy pathway here. Since the first step is endothermic, it means the transition state is going to be more stable. The carbocation is more stable. That means the transition state by Hammond's postulate will also be more stable. Okay, so that gives us, that's the ortho. And what we're going to see is the same thing is going to happen with the para. And then we're going to go here. And then we're going to get an extra resonance structure. I'll just draw it this way. I could have drawn this as my 3rd structure, but I'm just going to do it right now. That looks like this. And you can see that once again, we have this extra resonance structure that's especially stable. That one here and this up top here. So let's circle that. We have a lone pair on oxygen, we have a positive charge, and there's our especially stable resonance structure. So the ortho and para always go together, and you can see that we're going to get a 4th resonance structure that's especially stable. If the group goes on in the meta position, there's only the normal 3 that we usually draw. So it will look like this. And then we can go here, and that will look like this. See, did I do that right? So we go here, then we go here, positive charge right here, and the nitro group here. So we don't have any especially stable, we don't have any especially unstable, we just don't have that 4th bonus very stable resonance structure. And that's why we don't get any meta attack when we have activating groups. So in the ortho and para case, we'll write this down below. In the ortho and para case, the extra resonance structure lowers the energy of the carbocation intermediate intermediate, and by Hammond's postulate, the transition state. The transition state leading to this intermediate. That's a lower energy pathway. Since this is a high energy of activation for that first step, it makes sense that the ortho and para pathways are going to be better. I also want you, so we're going to have one of these mechanisms on the test. I usually have one where there's substitution already on the ring. So just to give you a little heads up on that. But what you want to make sure that you do is you check when you're doing resonance structures, because you'll get 2 points per resonance structure, that you don't duplicate, that you don't draw extra. So what you want to look for is, here's the incoming electrophile. The positive charge when it's in the ring is going to be in both ortho positions. Here, ortho to the nitro on the left, ortho to the nitro on the right, and para to the nitro. That will always be the case. So up here, here's our incoming electrophile. Ortho on one side, ortho on the other side, and para. So do a double check after you draw your resonance structures to make sure that you haven't made any mistakes, because if you draw extra resonance structures that are incorrect, they cancel out ones that are correct. Okay? So keep that in mind. So that's rule 1. Ring activating substituents or ortho-para directing. All right, so now let's look at rule number 2. This is for deactivating. And then we're going to talk about a third category, and that would be the halogens. So now notice that since I already have the skeletons for the resonance structures drawn here, notice that we don't have extra resonance structures for any of them. We have 3 for every one. And this time I'm just going to use generic electrophile here. So I'm going to do, I'm going to put the electrophile here. That's ortho attack. And then I'm going to do meta using that same double bond. Now I'm putting it in the meta position. And here I'm going to have to use this double bond on the bottom to attack the electrophile. And that will put the electrophile in the para position. So look like that. And then let's throw in on the rest of the double bonds here. Positive charge will be right here. And then we're just going to go crazy drawing resonance structures here. So I can move this over here. I can also go over here on this side, making sure not to duplicate. Does anybody see a problem with that third resonance structure I just drew? We've got 2 positive charges right next to each other, right? 2 positive charges on adjacent carbons. Very unstable. So we drew 3 resonance structures, but one of them is particularly unstable. So we'll circle that bad one here. And ortho and para always go together. So what that means is that we're going to have one, when we attack in the para position, we'll have that same thing, and we're going to get that right away here. That's going to go right here. There's our especially unstable one, right here in the middle. So here and here. And then in the last one here, we'll just have the double bond go in the other ortho position here. So it will look like this. So when we have ring deactivating substituents do electrophilic aromatic substitution, the best one, I didn't finish the meta, let me finish the meta. The best one is the meta. It's not especially stable, but it is also, let me fix that. Oh, no, that one, gosh darn it. So we're going to go here. So we'll have the positive charge here, double bond here. We have it in one ortho position. Let's put it in the other ortho position. So we don't have any especially stable, but we also don't have any that are, we have two that are especially unstable. Did you have a question over here?
Yeah, you mean adjacent species, not carbon.
On adjacent, yeah, atoms. Let's change that to atoms. Thank you, I appreciate that. On adjacent atoms, we'll just, on adjacent atoms, yeah. Okay, so in this case, the meta attack is better. Because we have, three decent, they're okay, but they're not great, but we don't have this especially bad one that we have in the ortho and para. So meta attack. No especially unstable. Resonance structures. So that's going to be our lowest energy carbocation. Lowest energy carbocation, then of course the lowest energy transition state. And therefore the lowest energy transition state. Questions on deactivated rings? So much more satisfying to actually know the reason why than to just memorize that ring deactivating are meta-directing. All right, halogens are in their own category. So I think it's easier for students when I put halogens in their own categories. So halogens are slightly deactivating but ortho-para-directing. So, and the reason is that with halogens there's a strong inductive effect. So halogens are strongly electronegative. That deactivates the ring. But they have weak resonance effects. They can donate their electrons, but they don't really like to donate their electrons very well. Halogens are not very basic, so they're not inclined to donate their electrons, but they can. So the lone pairs donate electrons back into the ring. To stabilize the carbocation intermediate. All right, and so they are slightly deactivated, but they are ortho-para-directing. And so I'm going to just show you, I'm not going to draw all of them, we just did that, and you can do that for yourself. But as you can see, we tack with the electrophile here, and we put the electrophile in the ortho position. We do have these lone pairs on bromine. Bromine's not super basic, so this doesn't really help very much, but it does help a little. So we get that extra stable resonance structure here. I haven't drawn all of them. There are two more, plus two more, which you can draw yourself. And we have this extra resonance structure, which is we don't get when we're in a meta position. Sorry about that. So extra resonance structure. when electrophile is in the ortho and para position. Not true in the meta case. So you should try this on your own. So the halogens are kind of they've got parts of deactivating, parts of activating. They're activated, they're like activating in that they're ortho-para directing, but they're definitely slightly deactivated. All right, so those are the three categories. It helps to kind of categorize them in the three categories so you can be able to figure out what your products are going to be. I want to talk about effective sterics in more than one substituent. So with ortho-para directors, para will predominate as substituents and incoming reagents get larger. It makes good sense. So if we do nitrate, if we nitrate toluene versus isopropyl benzene, here we get 58.5% ortho and 37% para. If it's isopropyl, we get 30% ortho and 62.3% para. So as you see, we go from 37 para with a methyl to 62.3% para with the isopropyl. Now, if that becomes a tert-butyl, we're going to get pretty much all para, as the tert-butyl group is much larger. This is actually, believe it or not, para is slightly favored here. And that is, and the reason is that methyl it does have some sterics involved with it. There are some sterics effect. How can para be slightly favored here? If there was no favorability, we would have statistically, we have 3 spots that can go. Right? So it could go ortho, para, or meta. And if there's 3 thoughts, 1/3 of the time it should go para, and 2/3 of the time it should go ortho. So if there was no selectivity, statistically there's twice as many ortho positions. So if there was no selectivity, we would get 66.6% ortho and 33.3% para. So as you can see, we do have a little bit more than 33%. So actually, it doesn't seem like from the numbers, para is slightly favored, and that's because methyl, it's not very hindered, but it has some steric hindrance, which would make more go into the para position. Questions on those two? So we want to keep that in mind when we're doing substitution on a benzene ring, because when we have ortho-para directors, we usually get ortho and para, and there's really nothing we could do about it, but the more bulky that group is, the more para. When the directing effects of 2 or more substituents conflict, so let's say we have electron donating and we have electron withdrawing. The one that is strongly activating and ortho-para directing determines the orientation of the new substituent. All right, so strong electron donating group, strong electron withdrawing group. We have a sulfonyl group going on, and it turns out that we're going to get ortho and para to the methoxy group. So the 2 products we will get. So in the battle of the directing groups, methoxy wins by far. All right, so here it is para to methoxy. Here it is ortho to methoxy. We do have another ortho position. Do you think we're going to get anything there? Right here is our other ortho position. And that's pretty hindered there to go in the middle there. So we don't tend to get that product. So you get ortho on the least substituted side, para here, but we wouldn't tend to get the one where there's a substituent right there. Now, if this was a methyl instead of a methoxy, nitro wins. Okay? If this was a methyl instead of methoxy, the nitro group, things are going to come meta to the nitro group. So when we have strong electron withdrawing and strong donating, the strong donating wins. If we have strong electron withdrawing and weak donating, electron withdrawing wins. Okay? So that, just to keep that in mind. And that leads us to additional considerations regarding substituent effects, and this is where it gets more complicated. All right. Methoxy, hydroxy, and amine substituents are more complicated than they would seem. Methoxy, hydroxy, and amine substituents are so strongly activating that halogenation is carried out without the Lewis acid catalyst, FeBr3 or FeCl3. Even without a catalyst, multiple halogenation is observed. So if we take phenol and we put it with bromine and no FeBr3, just water as a solvent, instant decolorization. So bromine's kind of like a deep, deep red, brown red color, and when you add it, it's going to instantly decolorize, which means that that reaction is happening very rapidly at room temperature, and all three ortho and para positions are filled. To monohalogenate phenol, run the reaction in nonpolar solvents such as carbon tetrachloride without added catalyst. And lower temperature also helps. We'll add lower temperature there. And you get ortho and para. All right, so got to be careful with phenol. The same goes for anisole too, where you have a methoxy group. So that's going to be the same as phenol. Amine substituents give multiple halogenation even at low temperature without added catalyst. You cannot stop at one halogen going on the benzene ring. All right, so we have a solution for this to make this reaction to sort of aniline's very highly activated, and what we can do is we can turn it into acid anilide, and that tones down the reactivity greatly. So this is strongly activated. And what we do to do that, we acylate the amine. So we're going to use acid chloride and pyridine. This is chapter 22 chemistry, so you do not need to know the mechanism for this reaction. I'm going to show it to you just so you can kind of picture what's happening. But when you do that, it's now moderately activated. So acid anilide, if you go back and you look at your activating groups, you will see that this is now moderately activated. And when we brominate, so it's now moderately activated, and it's pretty bulky, isn't it? So we're going to get like about 95% para. I'm going to get maybe 5% ortho, 95% para for this reaction. Okay, so it's 5% ortho, 95% para. So I do need to put my bromine there, don't I? So 95% para. So this is sterically hindered. Therefore, mostly para. And now once we're done with that, putting that bromine on, we can take that acyl group right off again. That is chapter 22 chemistry. This is a hydrolysis. That's a hydrolysis. You do not need to know the mechanism. You will know that soon enough when you get back here to start the third quarter of OChem. And so what that does is gives us aniline. Back again with one bromine on the ring. Okay, and that's important because once those bromines are on there, there's nothing you can do to get them off. So if you just want one bromine, you have to go through this long strategy to do this. I do want to show you how the amine is converted to an amide. It's an addition elimination that's similar to the mechanism for thionyl chloride. Let me show you. You don't need to know this mechanism, but some of you need to see this. It helps you to understand what's going on, and that makes it easier to remember the reaction. Okay, so thionyl chloride mechanism, remember there was a sulfur there, very similar to this. We did addition. So hopefully this is triggering the memory of that reaction from the first midterm. All right, and then what happens after that? The electrons on oxygen come down and we kick off chloride. So this is like the tosyl chloride mechanism. This is like the thionyl chloride mechanism. We do have a positive charge on the nitrogen, and that's why we have the pyridine, to deprotonate that nitrogen. So this is not really anything too difficult, but technically it is material from 51C, so I will not be asking you this mechanism. And then, of course, the last step. So if you draw this right under the thionyl chloride mechanism, you'll see how similar it is. And in the last step, we deprotonate with pyridine. So that's how we acylate. So definitely you want to get it straight in your mind. To acylate the nitrogen, we use acyl chloride and pyridine. To actually put the acyl group on the benzene ring to do Friedel-Crafts acylation, that's the acyl chloride and what? AlCl3, right? So two different things. With pyridine, so we have the acid chloride here. Acid chloride with pyridine puts it on the nitrogen. Acid chloride with aluminum trichloride puts it on the benzene ring. So definitely want to make sure you get those straight in your head. All right, questions? Anybody? Lots of problems with aniline. A lot of problems with aniline. That leads us directly into Friedal-Crafts, alkylation, and acylation. Lots of problems with Friedal-Crafts, too, that we're going to have to keep in mind. All right. So we'll use ethyl bromide, AlCl3. We're going to put an ethyl group on the benzene ring. Hopefully that is familiar to you by now. All right, now let's say we start off this reaction by forming one molecule of this, and then we have a bunch of this and one molecule of this. Which of these rings is more activated? Once we put that ethyl on, that's more activated. So what that means is the remaining ethyl chloride and aluminum trichloride is more likely to go onto this ring than that ring. Because this is activated, that's not activated. Okay? So what we end up getting, if we're not careful and we don't take steps to avoid this, it's going to keep going. Now we've got two activating groups on the ring. That ring is now more activated than the one ethyl group on there, which is more activated than having no ethyl groups on there. So we're going to get this, we're going to get ortho, we're going to get tri-substituted, and we're going to get tetra-substituted. Big problems here. All right, so the whole thing is about, this is an activating group. So therefore the product is more reactive than the starting material. All right, so how do we avoid this problem? We actually can't avoid this problem by using a large excess of benzene. Solution, use large excess of benzene. All right, so rather than using a one-to-one equivalent here, we're going to use a large excess of this. So maybe 1,000 times more than that. So that what that means is that, remember when we have the chloride attack the aluminum, we get that activated electrophile. It's more likely to encounter a benzene than it will to encounter one of these guys, or one of these guys, or one of these guys. So that's a way around that. So use a large excess of benzene if you, for Friedel-Crafts alkylation, if you just want one group going on. So just keep that in mind for the exam coming up. Questions on that? Anybody? Questions? Do we have that problem with Friedel-Crafts acylation? Do we have a problem with more than one acyl group going on? Anybody? No, because it's now deactivated. So product is deactivated. Therefore, over-alkylation is not a problem. Or I should say over-acylation is not a problem. So we have to worry about it with alkylation. We do not have to worry about it with acylation. Yes?
How would we indicate excess of benzene for the...
You can write excess just right below it. Okay? You can use it as a solvent, which means there would be a very large excess of benzene. All right. Problem with both Friedel-Crafts acylation and alkylation. So we've already encountered one problem. Alkylation goes overboard. We get over-alkylation. Problem number 2. Deactivated meta-directing benzene derivatives and aniline derivatives give poor yields of Friedel-Crafts products and should not be used in this reaction. All right, so that's a big problem. That really limits us. Deactivated meta-directors. Cannot undergo Friedel-Crafts, which I'll abbreviate FC, Friedel-Crafts reactions, and I mean alkylation and I mean acylation. What about halobenzene, that third category? Are those okay for Friedal-Crafts? What do you think? Well, it says here deactivated metadirectors. Halobenzenes are okay because they're deactivated orthopara-directors. Halobenzenes, okay, because they are deactivated, but orthopara-directing. It has to be both. So we want, make sure you look for both of those things. Deactivated metadirecting. So halobenzenes are okay. Halobenzenes can do Friedal-Crafts, and none of these guys can. So why aniline derivatives, though? Why? Because that's super activated. Here's the problem. This is an electron donating group, right? If you add acyl chloride and AlCl3 to that, what is the strongest base that you have there? Nitrogen. Nitrogen's the strongest base, remember? So here's our reactivity, CNOF, ClBrI. In order to do Friedal-Crafts, we have to have the chloride attack the AlCl3 and come off. Chloride does not have a chance because we've got increasing basicity this way. So the nitrogen is the one that's going to attack the AlCl3. And let's look at what happens once the nitrogen attacks the AlCl3. What happens to the nitrogen? It actually almost looks like this guy, right? Now the nitrogen has a full positive charge on it. That's a strongly deactivated metadirector now. So we've just turned this strongly activating into a strongly deactivated metadirector. So let's label that. This is strongly activating. Strongly deactivated. Strongly deactivated plus a metadirecting. So therefore, no Friedal-Crafts. Okay, so aniline is not working really well for us here. But we actually do have a solution for this. The same solution we had for the aniline when it was putting too many bromines on at the same time. Acylate it. Okay, so here, let's get this straight here. When we use the acid chloride and the pyridine is going to put this group on nitrogen. When we use the acid chloride and the aluminum trichloride, this group is going to go on the benzene ring. Want to get that straight here. This is going on nitrogen. So this is the one that's like the thionyl chloride reaction. This is the electrophilic aromatic substitution. So what we can do is acylate Now we can do Friedal-Crafts. And the reason we can do Friedal-Crafts is this nitrogen right here is no longer super basic. Let me scroll down so we can compare the two. This nitrogen don't do it that much. Okay, so this nitrogen right here is super strong base. This nitrogen right here, not a super strong base. Why is that? Much weaker base. Why is that? This lone pair would much rather kick in onto this oxygen here. Okay, so what happens is that this guy is kind of tied up in this resonance here. If that nitrogen takes its lone pairs and puts it on oxygen, the oxygen gets a negative charge, and oxygen loves having a negative charge in a resonance structure. So that nitrogen is not very inclined to attack the AlCl3 when it's got this friendly neighborhood oxygen right here it can throw its electrons onto. So this one actually will do Friedal-Crafts. So what happens in that next step? Where is this group going? Ortho or para? Mostly. Para, because this is pretty bulky. All right, so there now the CH3 is going, acyl group's going on the benzene ring, mostly para. About 95% para. And now we're ready to take that acyl group off again. We're just hydrolyzing it. So just remember, once that acyl group's on there, to get it off, we hydrolyze. So acid and water, followed by base to deprotonate the nitrogen, which will be protonated under those conditions. And we've actually found a roundabout way to do exactly what we would like to do. So we kind of have to do this roundabout way here. Questions on that example? Anybody? All right. And guess what? Aniline has more problems. We're not done with problems with aniline. All right, problem number 3 with aniline. Nitration. Okay, should work. Why? What's going on here, right? Why can't that work? Problems. Nitric acid is a strong oxidizing agent. And primary amines are easily oxidized. When you have a powerful oxidizing agent and you mix it with something that is easily oxidized, you can get an explosion, and you can get an explosion if you do this reaction. Explosion, if you don't get an explosion, you get tar. And that's where, and you guys probably haven't run a reaction where you get tar, but you run a reaction and you think everything's going to work, and you end up getting this tar-like substance in the bottom of your flask that's black, and usually means that your reaction has done not what you want it to do, and it's something that goes immediately into the waste container most of the time. All right, so we don't want to do that. It doesn't work. Now, if you have this one here's a tertiary amine, that will work very nicely. Where will the nitro group go? So this is not a primary amine, so this is okay. Where's that nitro group going to go? You think para? What's going to happen to that nitrogen as soon as you put it in concentrated nitric acid, concentrated sulfuric acid? What are the fastest reactions of all? Yeah, so what's going to happen is we're going to protonate this. Now that's an equilibrium that's going back and forth. So what we end up getting is the major product is actually the meta product. But you also will get the other ones depending on which state you're in here when in this equilibrium. Okay, so you're going to get you can get some orthopara, and you're also going to get some meta here. All right, so that's, and this should be NH2, sorry, let me fix that. NO2, yeah. All right, so that will work. It will not give you exactly what you want because you're going to get some ortho and para. But if you have acid anilide, it nitrates very nicely. Okay, so I know this works because we do this in my majors honors lab. And you get about 95% nitro in the para position. That's your major product. All right, so if you have a primary amine, if you have aniline and you want to nitrate it, you have to acylate it. So we're going to do the same exact thing that we've been doing here. We're going to acylate this. That tones down the reactivity of that nice nitrogen immensely, because now that lone pair likes to hang out on oxygen in that resonance structure. And then we nitrate, and so then our nitro group is going to go on in the para position mostly. So this is going to be the major product. And then we hydrolyze. H3O plus H2O, heat. We'll talk about this reaction next quarter, and you will know the mechanism for this. It's not that hard of a reaction, but you'll get a protonated amine because you're in strong acid. And so that's why in the last step you want to you do a basic workup to give you aniline with the nitro group in the para position, without any explosions, without tar. So it's just a little bit longer steps, but it works. It actually works. It actually gives you what you want. Questions? Anybody? All right, we'll stop right there, and we'll talk about reactions of substituents on benzene next time.